Hello everyone. Through this video, I am trying to give you certain problems which would make you consolidate the elementary concepts that are required for the understanding of the subject of network analysis. There are certain laws and principles which are to be thoroughly understood so that you can solve complicated problems of network analysis. So through this video, I'm trying to just check. So all you have to do is read the problem, take a pen and a paper, have your calculator with you, try to solve these problems on your own. You pause the video, solve the problem on your own, then you can play the video completely and cross-check the results that you have got with what is being obtained in the video. If they match, fine, it's successful. Simple elementary problems I have taken up. Okay? This is the first problem. In the circuit shown in figure below, find the value of unknown resistance R if the voltage across 500 ohm resistor is 2.5 volts. All the resistance values in the figure are in ohms. Okay, this is the problem given. I have given the network and I have written the values. So we are supposed to find the value of R. That is our objective. So you need to see what is this. What is R? This is what is to be determined. So how do we do this problem? What would it require to solve the problem? The basic concepts that are required are very, very simple. You need to understand, you need to know Ohm's law, fundamental Ohm's law, you should know to solve this problem. And number two, you need to know the combination of resistances. So what do we understand by resistances in series and parallel? And at the most, you would require Kirchhoff's laws, both the laws. That is your KCL and KVL. So all these three things we have studied in our basic electrical engineering in our first semester. Otherwise also, I have covered it in my network lecture number 3. If you can look into lecture number 3, if you remember lecture number 3, then you remember that we have discussed the basic concepts of resistance. Okay, so we will see as to how to go about this problem. Okay, let me erase this part. Now, coming back to the problem, we are supposed to find R. How do we find R? So in order to know the resistance, value, you need to know two things. That is, resistance equal to voltage upon current. So if you want to know R, you need to know the voltage across this particular terminals. That is, you need to know this voltage. I'll call this voltage V1. I will call the current here I1. If by some way I can get V1 and I1, I'll be able to find out what is the value of R. Okay, how do we do? What is given in the problem, if you can see, he says the voltage that is across 500 ohms is 2.5 volts. So I will call this voltage V3. This is equal to 2.5 volt. This is what is given. Okay. This is what is given to us. I will call this voltage V2. I'll name this voltage V2. Or the potential difference between these 2 points. Okay? How does the current flow take place in this network? I will just try to look at that. The current starts from the positive of the battery and it has to come back to the negative of the battery. That is the basic orientation of the current. So current would start from the positive of the battery. It would flow here in this direction. It will come to this node or a junction. I will name this junction as, let us say, I will take this color. I will call this junction A, and I will name this junction B. Okay, so current will take that path. I will call this current as I. The current will come up to point A. After coming to point A, to come to B, it has got two paths to take. One is the current can go this way, come to B, and the other can take a path like this and come to B. Okay, so it's clear that at point A, the current divides into two. One is I1, another current, I will name it as I2. This is I2. I2 will come here. And I will go back. I1 plus I2 is I. Okay, so I1 and I2, they recombine and I is formed, and that current returns back to the supply. So it's very clear that current breaks at A and recombines at B. So obviously the elements that are connected between A and B are in parallel, because current is dividing at one point and recombining at the other point. Okay, that's one aspect. The other observation is that the current that flows through this 50 ohm resistor, that is I2, will continue to flow through 500 ohm resistor. That means 50 ohm and 500 ohm, this one and this one, both carry the same current I2. That means this 500 and this 50, they are in series. So this network can also be reduced into a simpler one. We will call this figure A. Okay, so we will write another figure for our better understanding. In this manner, I will write this figure. I suppose you would appreciate if I write it this way. So this network can also be written like this, whereas this point is my A, this point is my B, and now the values of resistance, if I have to write, this is my R, this is my 550, and this now is 550. This current is my I1, this is I2, this current is I1, this current is I2. Okay, the voltage here is V1. This is V1. I'll write this V1 here. That's my V1. And this, as usual, is 12 volt. This is given 12 volt. Positive, negative. Okay, these two circuits are same. What we've done is this 50 and 500 we have combined and made it as 550, because 50 and 500 they are carrying the same current I2. So this much we have done. These two networks are same. This is my figure B. Alright, now coming back to the problem, we have to find out R. To find R, we know we need to get V1 and I1. How do we go about it? See, we know this voltage to be 2.5 volts. You know the resistance to be 500 ohms. Can we not get the current I2? The current I2 can be evaluated as V3 divided by I2. This is equal to 2.5 divided by, that should be 500 and 500 ohms. Okay, V3 divided by 500. This is 2.5 divided by 500. This comes out to be, how much is this? 0.005 ampere. This is also equal to 5 divided by 1000. We can write it this way. This is equal to 5 into 10 to the power minus 3 ampere, which is 5 milliamp. So you can take this value, or you can take this value. All are the same. Okay, we are able to get the current I2. So current I2 is also flowing through this 50 ohms. It is also flowing through this 50 ohms. Okay, and now this current I2 is known to us. We have evaluated this to be 0.005 ohms. Okay, now what is the potential difference across V2, across 50 ohms? V2 equal to, what is V2 equal to? V2 equal to the resistance times the current. It is 50 into I2. So that comes out to be 50 into I2 is 0.005. This is equal to 0. If you have to have calculators to calculate it to do this. So this is V2. So we have evaluated V2. Okay. So V2 is known, V3 is known. Now can we not get V1? What? V1 is the voltage here. It is same as the voltage across this 550. This is same as V1. Right? Is that okay? That voltage can be computed. What is that voltage equal to? So V1 equal to V2 plus V3. That is V2 is 0.25 and V3 is 2.5. This comes out to be 2.75. Okay, that is what is your V1. The voltage across R as well as across 550, because they are in parallel. Can you not see? R and 550 in figure B, they are in parallel. It's very clear, very evident. So you're able to get the voltage across that particular combination. Okay. Now, what is the voltage across this 550 ohms? This 550. I'll mark that also. I will use the same color for voltage. So I'll call this voltage as V4. Which voltage? This potential difference. This is V4. Okay. What is V4 equal to? How do we get that? V4 equal to, if you can apply simple KVL principle, V4 equal to the applied voltage 12 volt minus my V1. Because V4 plus V1 should be equal to 12. V4 plus V1 equal to 12. Simple KVL. In other words, V4 equal to 12 minus 2.75. This comes out to be 9.25 volt. Okay. So this is the voltage across this 550. Why am I finding out? Because I need to know the current through it. Therefore, I equal to V4 divided by 550. V4 is how much? 9.25 and this is 550. How much is this equal to? If you can calculate this comes out to be 0.018 ampere. This is the current I. Okay, the current I is equal to 0.018. I will use my calculator, and you can also take out your calculators, compute the value. Instead of relying on my answers, it's preferable, it is expected that you use your calculator and then you also compute. sorry, this comes out to be 0.0168 amperes. This is my I. Okay, why did I find I? Because I am interested in VI1. I am interested in I1. I know I2. I know now I can get I1. No, I already know V1. If I can somehow get I1, I'll be able to get R. That is my objective, right? Now, therefore, I1 equal to I minus, what is that current? I2. Okay? This is 0.0168 minus, what is I2? It is 5 milliamperes. That is 0.005. Right? So all I have to do is this subtraction we need to compute, and what we get is the current I1. This is equal to 0.0118 amperes. So this is my I1. So now I know the current through R, which is I1. I have computed the voltage across R, which is V1. So we can now easily do what is the resistance. Therefore, R equal to V1 upon I1. Okay, what is V1? V1 is 2.75. So we'll substitute that value. 2.75 divided by 0.0118. This comes out to be, what is the value? You can compute this. You can use your calculators and then you can do this. This comes out to be 233.05 volts. This completes our problem. Therefore, we will write the final result in this manner. The unknown resistance capital R equal to 233.05 ohms. This completes the problem. The problem is pretty simple. Okay? The problem is simple. Is that understood? I only hope that you understand this problem. See, the best practice that you can have while solving these networks is that you try to put the polarity. That is another feature that you can put. What I mean to say is, when current I flows through this 550, it will create a positive polarity here, it will create a negative polarity on the side, because current flows from higher potential to lower potential. Similarly, the polarity of V2 is in this manner. The polarity of V3, the top end is positive, the bottom end is negative. Here in R, end A is positive, end B is negative. You can do this way. You can even put this polarity so that you can have your KCL, KVL properly written. Okay, this is a very simple problem. We may do similar problems. I will try to make more videos based on these problems, some problems of similar nature, so that you can practice and you will be able to do little complex problems in network analysis. Having done the first problem of determining the unknown resistance in a given network, we will try to go ahead with another simple problem, which goes this way. Determine the value of resistance R and the current through it if the current through the branch AO is 0. This is what is given to us in this problem. The network is being written. You can see the network. This is how the network is. So we are supposed to find out the value of R and also the current through R. How do we go about this problem? See, what he says in the problem, you have to see very clearly, understand it very clearly. He says there is no current in this branch A and O. So we need to write the current. We will try to express the various quantities in this network. Let me say that this current is I. Okay, from the positive of the source, I ampere would come to, let me call this point, this terminal B and this terminal C. Now I will try to understand the current distribution. Current will come up to B. What is the course of this current? Current somehow has to come back to C. What are the possible ways in which the current can come back to C? So at point B, current can see two paths. It can take a path here. It can take a path here. All right. So I will call this current I1 and I will call current through 4 ohms to be I2. Now, I1 will reach A, I2 will reach O. Okay, now what will happen further? Further, if you see, in the given problem, he says there is no current through AO. Current through AO or current through this X is 0. So, current through this is 0 means neither current from O will go towards A nor the current will move from A to O. Or in other words, it is as good as this AO not being there. Or simply, you can replace the resistance X by an open circuit. It would mean the same. So obviously, if you go ahead, current I1 has to take this path. This current is the I1. And the current I2, which comes to O, cannot take the path through X. So it will go to this and come back to this. This is my I. This is how the current is going to take its path. This is how the current is going to flow. Or in other words, we can write this network simply like this. I can write the same network in this manner. Okay. Aren't these two same? This is 2. This is 2. This is 10 volt. All the resistances are in ohms, so I don't write ohms everywhere in the network. This has to be clearly understood. This is 4. What have I done? I have removed this X, which is connected between A and O. I can easily do it because in an open path, the current will not flow. Our current is 0 in an open path. So here between A and X, A and O, we had X. This X is now being removed. This is how the network becomes. All right. So how do we find out now R? If you can see this network, it is Wheatstone bridge under balanced condition. Are you able to recollect that it is a Wheatstone bridge under balanced condition? What I mean to say is there is going to be, it is something like if you connect a galvanometer here, the galvanometer will read 0. This is a bridge under balance. So if you can remember the formula, we write the formula like this. We write this as R1, this is my R2, this is our R3, this is our R4. So we write the balance equation for Wheatstone bridge. So bridge under balance. Bridge under balance means the galvanometer doesn't carry any current. So we say R1 by R2 equal to R3 by R4. This has to be true. So by substituting the values, what we get is 1 divided by 1.5. I am substituting. This comes out to be R3 is 4 and R4 is capital R. Thereby, capital R is equal to, on cross multiplication, 1.5 into 4, 6 ohms. That's it. We are able to get R. But the thing is, in order to apply this, One is you must be able to remember this formula quite well. Number two, you should know which element is R1 and which element is R2, which element is R3 and which element is R4. If you are confused, you're gone. You cannot solve the problem properly. You will end up getting an incorrect answer. Okay, I don't remember, but what do I do? If that is a question, well, we will go by the first principle. We will try to do the first principle and solve. Okay, I will now remove this part, or let it be there, let it be there. Let this part be there. Okay, so we will try to do this by applying first principle. What is that? We have named this point as B and this is my C. Okay, these two networks are same. My figure 1, this is figure A, or figure 1 is same as figure B. They're same, they're identical. They're just the same, drawn in a different manner, that's all. Now, we will try to apply the first principle. What is that first principle? We have written the currents, right? I'll take the same color yellow so that my currents are the same. This is I1. When there is no current through the galvanometer, I1 will take this path. Current is I2 here. Obviously, the current will flow here and it will go. Okay? In other words, if the potential difference across A and B, if it is equal to the potential drop across B and O, then A and O are at the same potential and then there is no current between the two. We will write that. What I mean to say is, for current through A and O to be 0, this is given, right? This is given, right? For this to be 0, the potential difference across 1 ohm should be equal to the potential difference across 4 ohms. Also, potential difference across 1.5 ohm should be equal to potential difference across R ohms. These are two equations I have. Equation 1, equation 2. Okay, what is potential difference across 1 ohm? How do we do? It is current times the resistance. That means the current is I1, resistance is 1, which is equal to potential difference across 4. 4 ohm is carrying I2 amperes of current into 4. This is my equation 3. Okay, equation 2, we will come to equation 2. Potential difference across 1.5. What is potential difference across 1.5? It is simply 1.5, that is resistance, multiplied by its current, it is I1, equal to potential difference across R. Potential difference across R is I2 into R. This is my equation 4. Now what I'll do is, I'll try to divide equation 4 by equation 3. What do we get? I2 times R divided by I2 times 4 equal to, on this side, 1.5 times I1 divided by 1 into I1. Okay, I1 and I1, I2 and I2, cross multiplication will give me R equal to 1.5 into 4, which is equal to 6 ohms. Alright. This is what, this and this are now same. Alright. So what we have done here, by this method, we have used simple formula. In this method, we don't remember what is R1. What I mean to say is, in this method, we do not know what is R1, what is R2, what is R3, what is R4. But we remember the first principle. That means for the current through X, R, current through the galvanometer in figure B is same as the current through X in figure A. To be 0, our point A, or the node A, and node O, they should be at the same potential. For that to happen, the potential drop across AB should be equal to the potential drop across BO, and the potential difference across A and C should be equal to the potential difference across C and O. That is what we have written as equation 1 and 2. On substitution, we get this much. Alright, this is done. Now what is the second part of the problem? Second part of the problem says you have to find the current through this R. How do we get the current through this R? It is now simple. In order to get the current through R, now that you know the value of R to be 6 ohms, you can easily get the current through R. How do we do? Now we will try to put the value of the current resistance in the network and rewrite the network. I will rewrite the network in this manner. The same network. I am drawing in a different, giving a different shape. That's all. It is the same network. Okay, it is the same network. What do I write? How do I write? Okay, so this is B. Okay, B. This is B. This is A. This is O. This is C. They're the same, right? What do I have here? This is 1 and 4. This is 1 ohm, 4 ohm, 1.5 ohm. Now this is 6 ohm. This is 10 volt and this is 2 ohm. So what are we interested? We are interested in knowing the current here, which we have called it as, this is my I1, this is my I2. We are supposed to get I2. Can we not get I2? It is so simple. Can we not get I2? It's a very, very straightforward and a simple problem. Okay, how do we do? Now this network is same as, this is same as, I will use my white color. This is same as, I can write it this way. This is one resistance. This is another resistance. I will combine the two, put it across 10 volt. This is 2. It's the same. This is 10 volt. How much is this? This is 2.5. This is 10 ohm. This is done. It's the same circuit. I've combined these two. Because same current flows. Okay? I1 is flowing through 1. I1 is flowing through 1.5. So the two resistors, 1 ohm and 1.5, it's carrying the same current, I1 amperes. So you can add it up. It comes to 2.5. 4 and 6, they carry the same current I2. So I've clubbed them, I've added them. Series resistance, 10 ohms. The remaining circuit is as it is. So this is my I. I will quickly do. This is I. This is I1. This is I2. We have to get I and then I2. How to get I? Now we will not simplify the network any further. We will simply write I equal to the 10 volt divided by 2 plus the parallel equivalent of 2.5 and 10. Okay, these two are in parallel. They are in parallel. That is this much. That gets added to 2. Okay, if you replace this yellow circle by one single resistance R, then R and 2 ohms, they are in series. R and 2, they come in series. Alright, so that is why I have added this parallel resultant to 2. So this comes out to be 10 divided by 2 plus, how much is this? This is 2.5 into 10 divided by 12.5, the sum of the two. How do we find the parallel equivalent of two resistors? The product of the two divided by the sum of the two. How much is this going to be? You can compute this using your calculator. It is a simple computation. Use your calculator and then you do it. Take out your calculator. Where is my calculator? I need to have my calculator. 1 second. Here's my calculator. Yes, I got my calculator. Okay, so this comes out to be, how much is this value? You compute this. 10 divided by, this is 2.5 into 10 divided by 12.5 will come out to be 2. The 2 plus 2 is 4. This is 10 by 4 or 5 by 2. 10 divided by 4 will make it to be 2.5 ampere. This is my total current I. I suppose this is a simple computation of Ohm's law. I need not have to elaborately tell. Okay, this is my 2.5. Now from 2.5, what I am trying to find out is, I need to find out I2, right? I need to find I2 because I2 is the current through the unknown resistance R equal to 6 ohms. We need to get I2. How to get I2? So I1 and I2 are two parallel currents flowing out of I. Okay, we will try to apply current division and find out I. I2 equal to I into, we will come to this figure, I into the resistance of the other branch, it is 2.5 divided by the sum of the two parallel resistances, that is 2.5 plus 10. This is the formula you have. This is 2.5 into 2.5 divided by 12.5. Okay, that is the total current that flows through R. Okay, how much is that? 2.5 into 2.5 divided by 12.5. This is 0.5 amperes. That completes the problem. Okay, therefore current through R, what is R? Current through R equal to 6 ohms is 0.5 amperes. That would complete the problem. We are supposed to find the unknown resistance, then we are supposed to find the current through that unknown resistance. Both we have done. Alright, so this is another problem that we have, a very, very simple problem. See, such simple problems will make you understand the basic concepts. Okay, I suppose I will stop this video here and maybe take up another problem in my next video.